Let's look at how to look at a table and see if there is direct or indirect variation. I've created two tables. We will look at both tables. If there is direct variation, there is a common ratio in the table. Okay, the common ratio will be y to x, okay, which really it's the slope. Okay, so let's take each ordered pair in our tables and find the ratio. Okay, so the first ordered pair will be 9 over 3, which is 3. The next ordered pair is 24 over 8, which is 3. And the third one is 30 over 10, which is 3. So we get this constant ratio. Oops. Constant ratio. Since we have a constant ratio, this is a direct variation. So let's look at the next table. Okay, we're going to check for direct variation. So we're going to look at the ratio y to x. So in the first one, we have 8 to 4.5, which is 1.7 repeating. The next one is 3 to 12, which is 25 hundredths. Okay, as we can see, our common ratios are not the same, or our ratios are not the same, so we do not have a constant ratio. Okay, so we do not have a direct variation. Now, to determine if it's an inverse variation, we look at x times y. So we're going to take 4.5 times 8, which is 36. We will take 12 times 3, which is 36. And we will take 2 times 18, which is 36. So, as you can see, we have a common product or a constant product. When this happens, we have inverse variation. So this is inverse variation. At this time, I want you to turn to page 573, page 573. Do problems 13 through 15 and 28 through 30. 28 through 30. Our objective for this part of the lesson is to use combined variation. Combined variation is a relationship that uses both direct and inverse variation. Let's look at okay. The volume V of a gas varies inversely as the pressure P and directly as the temperature T. A certain gas has a volume of 10 liters at 300 degrees Kelvin and a pressure of 1.5 atmospheres. If the gas is compressed to 7.5 liters and heated to 350 degrees Kelvin, what will the new pressure be? Okay, so this is an example of a combined variation. Okay, we have the volume V. It is varying inversely as the pressure P, so that means we have some value K divided by the pressure P, and then it's acting directly as the temperature T. So the constant of variation K is being multiplied by the temperature T. So we have V equals K times T divided by P. Okay, now a certain gas has a volume of 10 liters. So I'm going to replace V with 10. We do not know the constant of variation. That's what we are looking for. Okay, we do know that the temperature is 300 Kelvin. So we replace T with 300. And we know the pressure is 1.5 atmospheres. So P is replaced with 1.5. Now, what I'm going to do is I'm going to think of it as 10 over 1. Now we have a proportion problem. Proportion problems are solved by looking at their cross products. Okay, so we're going to take 1 times 300K to get 300K, and we will take 10 times 1.5. Okay, so now we have 300K equals 15. Divide both sides by 300. And that gives us a constant that gives us the constant of 1/20th. 1/20th is 5/100ths, which is 0.05. Okay, now that we have our constant K, we can come up with our equation of V equals 5/100ths times the temperature divided by the pressure. Okay, now if the gas is compressed to 7.5 liters, so that means the volume is reducing from 10 liters down to 7.5 liters. Okay, so we're going to replace V with 7.5. Okay. And we are increasing the temperature from 300 Kelvin to 350 Kelvin. We want to know, how does this affect the pressure? Okay, so in this case we're looking for the pressure. Alright, again, I'm going to take 7.5 over 1. Okay, and we're going to rely on cross products. So 7.5 times P is 7.5 P. Then we're taking 1 times the product of 5/100ths and 350. Okay, so 5/100ths times 350 is 17.5. Is 17.5. So now we take and divide by 7.5, and P is 2.3, repeating. Okay, so if the gas is compressed to 7.5 liters and heated to 350 Kelvin, the new pressure will be 2.3 atmospheres.